Dinosaurs, their secrets revealed. For the largest creature to walk the earth, was breaking the sound barrier foreplay to sex?
So I think these dinosaurs may have moved their tails supersonically to get a date.
Then see through the eyes of a killer. Did T-Rex stalk the prehistoric jungle with the eyes of a hawk? And after all that eating, dinosaurs dropped mountains of dung, loaded with clues.
Well, you know that old statement, you are what you eat. That holds today as it did millions of years ago.
Unlock secrets from fossilized feces and become a dinosaur detective. Are those prehistoric footprints evidence of one dinosaur attacking another?
I would expect this to have the skid mark from hell.
From love to death, the secret lives of dinosaurs. Next. The world of dinosaurs, a mysterious place once wrapped in silence. But now, for the first time, dinosaurs are breaking their silence, speaking to us over millions of years of time. And scientists, using the latest computers, are listening and bringing life back to ancient fossils. In giving dinosaurs their true voice, researchers are making fascinating discoveries about what sounds dinosaurs may have made from head to tail. And in tracking these sounds, scientists are shedding light on the most intimate realm of dinosaur life, their mating habits. The search for dinosaur sounds begins in the remote quiet of the San Juan Basin of northwestern New Mexico. Paleontologist Tom Williamson of the New Mexico Museum of Natural History is looking for dinosaur fossils. 75 million years ago, this high, dry plain was a lush tropical jungle, the perfect habitat for Parasaurolophus, the dinosaur known as the cow of the Cretaceous period.
Parasaurolophus was a crested duck-billed dinosaur. He would have been about 30 to 35 feet long, would have weighed 2 to 3 tons, stood maybe about 10 feet high at the hips, and the length of his skull from the tip of his snout to the tip of his crest would have been about 6 feet.
The unique crest adorning the head of Parasaurolophus puzzled paleontologists. Many believed there was a simple hollow tube inside the crest that the dinosaur used to make sound. So scientists dubbed Parasaurolophus the trombone dinosaur. But a better understanding of the crest lay hidden in the sandstone of the New Mexico desert.
Well, this is about the area where we found the new specimen of Parasaurolophus. And when we first encountered it, there was just a tiny bit of it exposed out of a sandstone, just like this. And when we finally uncovered it, it turned out to be, about 5 or 6 feet long. So it would have fit in a circle. About like this. This is the crest of the new specimen of Parasaurolophus we recently found here in New Mexico. It's quite a large animal. The skull would have extended from here. This is about where the tip of the beak would have been, all the way back to the tip of the crest. This is close to about 6 feet in length. And when this animal inhaled, it would have drawn air in through its nostrils about here and pulled that air through the air chambers inside of the crest all the way down and then through here into the skull.
Williamson arranged to have the crest CAT scanned at an Albuquerque hospital. This advanced X-ray machine allowed them to see inside the fossil without damaging it. the CAT scan produced a series of 350 cross-section images of the crest. But to make sense of these images, Tom Williamson needed more powerful computers than he had at the museum. He called on computer expert Carl Dygert of Sandia Labs. Dygert used his advanced imaging software to assemble the 350 two-dimensional slices into one three-dimensional model of the internal structure of the crest.
This is the end result. This is our understanding of the internal plumbing diagram. This is the structure of the sinuses in Parasaurolophus.
That internal structure is much more complex than scientists had previously suspected. Instead of just one looping passageway, there are three main tubes. After accurately mapping out the inside of the crest, the scientists measured the length of the tubes to determine what note the dinosaur would have sounded.
The length of the instrument sets the note that it plays at, the register, the high note or low note. This sounds at a first octave D, and that first octave D is determined by the length of this tube. Basically, sound worked the same 75 million years ago as it does today. So by measuring the length of his sinus passage, we know the note that he sounded.
Parasaurolophus would have created sound by breathing in through its nostrils, drawing the air through its crest, and then bellowing out of its mouth. But fossils almost never preserve soft tissue, so scientists don't know if Parasaurolophus had vocal organs. Without vocal cords, the dinosaur would have used the crest as a simple resonator, creating a low-frequency sound, similar to blowing air over the top of a bottle.
So I'd like to play for you now a sound that Parasaurolophus could have made.
For the first time in 75 million years, the crest roared back to life.
Well, the sound that we reconstructed, it was just something that we had never heard before, and it was a visceral sort of a sound, and something that you would feel more than hear.
But if Parasaurolophus did have vocal organs, the dinosaur would have had a much greater range. It would have been able to vary pitch, resulting in sounds like these, which are more like bird calls. Once they discovered the basic crest sound, the scientists could use the computer to improvise what songs Parasaurolophus might have made. The computer playing the crest call is at the forefront of the information age. But the information it's using is prehistoric.
The fossil told us this sound. We didn't create this. This is as predicted from the anatomy, from the fossil record.
This haunting sound carries an ancient message to the scientists who breathed new life into the crest of Parasaurolophus.
Well, I suppose he's talking to us over 75 million years.
And what is Parasaurolophus saying? The scientists might want to ask the elephant, a modern animal who communicates everything from danger to desire with a low-frequency rumble.
We can only look at how modern animals use sounds. They probably use them to communicate with each other. And perhaps they were using them to attract mates, or to warn others of approaching danger, or to coordinate their movements as they traveled great distances.
This low sound in that low register physically carries very well. The lush vegetation absorbs sound quickly. Higher pitched sounds won't carry nearly as far. So it may be that it evolved so that they could find each other for mating or sound warning calls.
The mating call of Parasaurolophus wasn't the only message of love echoing across the ancient landscape. the largest creature to ever walk the earth may have also been the loudest. For Apatosaurus, breaking the sound barrier was merely foreplay. Cyber paleontologist Nathan Myhrvold, the head of technology at the Microsoft Corporation, is using more than just a computer to study this giant beast.
Should be able to do this so much better, but I'm not a sex-crazed apatosaur. Apatosaurus was a huge animal. It was 90 to 100 feet long, of which about half of that, say 45 feet, was in the tail. They had very long, thin necks, giant body that would crest at the top, maybe 15 or 20 feet off the ground. They'd weigh somewhere between 18 to nearly 40 tons, depending on the estimate. Male elephant, big one, is maybe 5 tons. So that's, you know, somewhere between 4 and 8 African elephants in a single animal.
To discover the biomechanics of extinct animals, paleontologists usually play with the fossil bones to see how they fit together and work. But the big, heavy sauropod bones make it virtually impossible for scientists to do this kind of work. Today, computer simulation allows Myhrvold to take big strides toward discovering what kind of moves the sauropods were capable of. Myhrvold was particularly curious about why Apatosaurus had such a long tail and what it could have been used for. When it was attached to its owner 200 million years ago, the tail of the Apatosaurus was impressive enough on its own, 40 feet long and weighing over 3,000 pounds.
And it would taper from an initial section that's maybe 3 feet across, giant thick tail. It would taper down to an end which wasn't much bigger around than my thumb. Why?
Myhrvold began his search for an answer by observing monitor lizards. In watching the monitor lizards, Myhrvold noticed how much their tails, in both form and function, reminded him of whips.
Whips have got a couple of key features. They start off with a very stiff section that you use to impart some momentum. They're thick, and they continually get thinner and thinner and thinner all the way down to the very end, which is extremely thin and extremely flexible. So if these dinosaur tails were whips, maybe they were noise-making whips.
But what exactly accounts for the sound of a whip cracking? The crack of a whip is a lesson in the laws of physics. Cracking a whip produces a wave, which travels down the length of the whip, from thick handle to thin tip. As that wave moves down the whip, the energy produced must remain constant. According to the physics formula, velocity equals the square root of the force of the whip divided by the mass of its radius. But for the energy to remain constant, the relationship between velocity, force, and radius changes dramatically.
Mass is dropping, radius is dropping, but the product of the three of them has to be constant. That means to compensate, velocity has to go way up.
How much is way up? By the time the wave reaches the end of the whip, it's traveling 1,300 miles an hour.
A whip like this typically goes around Mach 2, twice the speed of sound. And that generates a sonic boom. That sonic boom is what we hear as the crack of the whip.
Myhrvold wondered if an Apatosaurus could flick its tail hard enough to produce a sonic boom. The idea seems unbelievable, but his computer model showed that Apatosaurus could crack its long, thin tail like a whip with just a fraction of the energy it took him to walk.
We determined that the kinetic energy required to crack one of these tails and make the boom is only about 17% of the energy it would take for the dinosaur to take one step forward.
That's because whips don't consume energy, they concentrate energy. If Apatosaurus cracked its massive whip-like tail, it would have produced much more than just a crack.
they were probably 2,000 times louder than a whip like this. That makes them about as loud as a large naval cannon.
But why would Apatosaurus fill the prehistoric landscape with the sounds of a full-scale naval engagement? The tail crack of the Apatosaurus may have been a demonstration of sexual prowess. Myhrvold thinks tail-cracking dinosaurs were interested in love, not war.
So I think these dinosaurs may have moved their tails supersonically to get a date.
So 200 million years ago, Apatosaurus would crack its tail to attract a mate. But what happened after the female Apatosaurus answered the sonic boom? How did the world's largest land creature mate without crushing its partner? Surprisingly, some paleontologists believe the giant dinosaurs copulated like their tiny cousins, the reptiles of today. The male's penis, normally concealed within, emerges during sex. The female lifts her tail, then the male throws one leg over her back.
By throwing only one leg over, you don't put all of the mass here. And then by curving the tail underneath, you get away from the problem that these giant tails would otherwise be in the way.
Scientists have also found evidence of a penile retractor muscle in sauropod fossils.
There's a bone called a chevron. It attaches to one of the first tail vertebrae down here. Maybe not the first, but one of the early tail vertebrae, which has an attachment point for a muscle whose function in life is, after sex, to reel the penis back in. On an animal like this, the penis is going to be pretty big, estimates of 10, 15 feet long. So you need to have a substantial muscle to reel it back in afterwards.
From the most intimate details of a dinosaur's mating habits to its loudest display of desire, dinosaurs are speaking to us across millions of years of time. And as paleontologists unearth more fossils and discover new ways to study them with computers, the secret lives of dinosaurs will be secret no more. "60 miles south of Dallas, the Paluxy River flows quietly through the gently rolling hills of central Texas. But lurking below the surface is the violent story of two dinosaurs. Preserved in stone at the bottom of the Paluxy River are 100-million-year-old dinosaur footprints, the round tracks of a plant eater, and the three-toed tracks of a meat eater. The tracks left in the mud of a prehistoric coastline preserve a moment in time, a moment that some experts say may have been a moment of death. The Paluxy River trackway may be one of the greatest finds in the history of paleontology, because it could be the only direct evidence left on Earth of how one dinosaur hunted another. But the Paluxy River trackway might have remained hidden in obscurity if it weren't for an eccentric fossil collector named Roland T. Bird. R.T. Bird was riding his motorcycle through Texas in 1938 when he heard stories of strange giant footprints in the Paluxy River near the town of Glen Rose. When Bird investigated, he quickly realized what a valuable find he had. As he began to excavate, one particular pair of tracks grabbed his attention. The three-toed tracks of a meat-eating dinosaur appeared to be running parallel with the large, round tracks of a plant-eater. Bird interpreted the tracks as evidence of the meat-eater chasing down and attacking the plant-eater. Bird cut the trackway out of the river, and parts of it were shipped to different museums. But many thought Bird's interpretation of the trackway as an attack was overly dramatic. So Bird's theory about the trackway died with him in 1978. The matter lay undisturbed until 1984, when paleontologist James Farlow of Indiana Purdue University began preparing Bird's autobiography for publication. In going through Bird's private papers, Farlow made a remarkable discovery.
This is the treasure that turned up in the Bird attic. This is R.T. Bird's chart of the Paluxy River dinosaur footprint site. And it documents the interaction of two dinosaurs, a big plant-eating dinosaur and a large carnivorous dinosaur.
By finding the Bird chart, Farlow had also rediscovered the mystery that had fascinated R.T. Bird. The mystery of what was missing from the sequence of footprints.
Okay, Bird noticed that there was good left-right sequencing of the meat-eater's trail until he came to this spot. Because here there was a right footprint, here there's another right footprint, but there's no footprint of the left foot there. What's going on here?
When R.T. Bird excavated the trackway in 1940, he thought the missing footprint was a sign of a violent assault by the meat-eater against the plant-eater. Jim Farlow explains Bird's attack theory.
And so he came up with a scenario in which the meat-eater about here actually grabbed onto the plant-eater, it physically attacked it, put down its right foot, but then got jerked out of its print and pulled through the air such that it wasn't even able to put down that left foot. It did a kind of involuntary little hop and came down on the right foot, and that's the hop scenario.
Some observers believe the tracks might have been made hours, days, or even years apart. But Bird thought there was no doubt the tracks were made at the same time because they turned together twice. Based on Bird's chart, Farlow supports part of Bird's theory, but not all. He believes there was a chase, but not an attack.
I think it's pretty clear that the meat-eater was following the plant-eater. I don't see any compelling evidence that they actually fought or grappled in these trackways. So it might be more accurate to say I see this as more a chase than an attack.
One reason Farlow thinks it was only a chase is because the plant-eating target, a dinosaur called Parasaurolophus, may have been too big for its attacker.
Parasaurolophus was a big, four-footed, quadrupedal, plant-eating dinosaur. It's a little hard to say exactly what its dimensions were, but might have been something like 50, 60 feet long from nose to the tip of tail. If it lifted its head off the ground, maybe 20, 25 feet, probably weighed something on the order of 20 or 30 tons, and it made footprints from the hind foot, the larger foot, a little more than 3 feet long.
But another man who has studied the Paluxy River trackway thinks he has the evidence to support Bird's attack theory. Paleo artist David Thomas of Albuquerque, New Mexico, is sculpting the head of Acrocanthosaurus, the vicious meat-eater he thinks attacked the much larger plant-eater.
The most likely candidate for the predator is Acrocanthosaurus, which is a large theropod that was in the area at the time. Theropod is a two-legged carnivorous dinosaur. This Acrocanthosaurus was about 30 feet long. His back was about 8.5 feet off the ground, his head probably a little higher than that. He probably weighed around 3 tons, and his track was 19 inches long.
In an effort to make his sculptures as accurate and realistic as possible, Thomas has spent years studying how animals walk. He knows the footprints animals leave behind offer clues about how they move. Because dinosaurs are related to modern reptiles, many experts assume dinosaurs walked like reptiles.
People thought that they walk like reptiles, which is they lead with the front leg on one side, follow with the diagonal rear leg, and then repeat the process on the other side.
Because a reptile's diagonal legs are moving together, the rear foot lands while the front foot on that side is still on the ground. This means a reptile never steps on its own tracks. But in studying the Paluxy River footprints of the big plant-eating dinosaur, Thomas discovered that the large, round back footprints of this giant sauropod often overlapped or obliterated its front footprints. This suggested the sauropod didn't walk like a reptile after all. It walked like a mammal.
In a mammalian walk, they lead with the hind foot on one side and follow with the front foot on that same side, so that both feet on one side are off the ground at the same time. This permits for the hind foot to come down and obliterate or impinge on the track left by the front foot. So there's no question, dinosaurs, quadrupedal dinosaurs walked like quadrupedal mammals.
Thomas thought that if dinosaurs walked like mammals, maybe they also hunted like mammals. So he studied how mammals pursue their prey, and he found they use remarkably sophisticated tactics.
Very frequently, the cat or hyena, whichever it is, will pick up the rhythm of the prey animal and match it step for step. Just go with it.
Matching strides with their prey gives hunters two advantages.
When he's in the same rhythm and step length as the prey is standing still relative to the predator, and he can then strike with great precision.
And with less risk of injury, a crucial consideration in a harsh environment.
The predator, a big cat, dinosaur, whatever, lives in a world where a broken leg is a death sentence.
When Thomas takes what he's learned about animal movement and applies it to the Paluxy trackway, he sees the big four-legged plant eater walking along, leaving its round tracks in the mud. The three-toed meat eater is following closely behind, stalking its prey in the same rhythm and stride as its target. When Thomas connects the footprints of the two dinosaurs, they form a symmetrical series of diamonds, right out of an Arthur Murray dance class.
But you have the 6 diamonds because these two animals are practically dancing together.
And Thomas, like bird before him, thinks it was a dance of death, climaxing in the meat-eater's lunging attack that left the missing footprint.
When you have two animals in the same rhythm for 20 consecutive steps, that's beyond coincidence. There's something going on there, and what's going on is an attack.
The attack scenario is compelling, but it's not accepted by all paleontologists. Jim Farlow doesn't believe it. He thinks if the missing footprint is evidence of an attack, then the next step should be anything but normal.
For one thing, if the animal had made a hop and come down on its right foot after leaving on the right foot, this is an animal that's a couple tons or more in weight, being jerked off its feet, lifted through the air, comes down. I would expect this to have the skid mark from hell. I just don't see anything like that. It's a normal footprint as best I can tell. So it makes me think that the hop probably did not happen.
But if the hop didn't happen, then why is the footprint missing? Jim Farlow offers a far less dramatic solution to the mystery.
Maybe the mud there was soupier than usual, so that when the animal picked up its left foot, assuming that it did put the left foot down there, it just collapsed inward and didn't preserve a track.
But Dave Thomas insists the missing footprint marks a strategy that was the beginning of the end for the plant eater.
A strategy that's used by modern predators against much larger prey It is to keep the prey moving and keep him bleeding. He's not trying to bring down that huge animal that's 10 times as big as he is right away. But if he can get it bleeding, keep it moving, sooner or later it will go down.
The tracks of the two dinosaurs turn to the right and disappear under the banks of the Paluxy River. Beneath tons of rock and dirt may lie more tracks, and perhaps even bones, that could solve the mystery of the trackway. Perhaps over time, the Paluxy River will uncover those clues. For now, Jim Farlow does not believe there was an attack. But it's a belief he'd put a reluctant bet on.
The way my luck usually runs, probably 50, 60 feet under the bank, there is a skeleton of a dead sauropod dinosaur with lots of tooth marks in it, and then footprints of a now very heavy meat-eating dinosaur walking away, taking very short, smug, self-satisfied steps.
The Oregon woods become the Cretaceous jungle in the mind of computer scientist and vision expert Kent Stevens. Stevens, a University of Oregon professor, imagines he's being pursued by Tyrannosaurus rex, the most feared creature in history. But this isn't just idle daydreaming. For Stevens, it's work. Envisioning what T-Rex could see may hold the key to understanding how T-Rex hunted. Stevens plans to unlock the mystery by looking through the eyes of the killer. For the first time, we will see the world as T-Rex saw it.
T-Rex seems to have all the hallmarks of a pursuit predator visually. And if you look at any specialization across different sorts of species, animals use the capabilities that they're specialized for. And if you think of T-Rex in its use of its vision for predation, it seems to me to have been an active predator.
But this portrait of T-Rex as a ferocious predator is not shared by all paleontologists. Looking at T-Rex's anatomy, they see an animal too slow to chase its prey, with forelimbs too small to grab its prey. To them, T-Rex was little more than an overgrown vulture, an opportunistic scavenger who let others do the killing before swooping in to steal the spoils. The paleontologists who see T-Rex as a scavenger argue that T-Rex's vision was too poor to allow it to hunt and chase its prey. But Stevens disagrees.
The movie Jurassic Park fired me up on the thinking about binocular vision and theropods like this T-Rex. The idea that it was as primitive as a frog and only seeing prey if they moved, I thought was a little on the silly side.
Scientists have found that eyesight is a key component in determining an animal's hunting strategy. Carnivores with keen eyesight, like a hawk or a cheetah, can hunt and pursue their prey. But a meat eater with poor eyesight, like a crocodile, can't pursue its prey. It's forced to lie in wait and ambush its victims. Was T-Rex a hunter or an ambusher? Kent Stevens suspected T-Rex had the good vision of a hunter. But just how could he see through the eyes of an animal that has been extinct for 65 million years? He decided he could map T-Rex's field of vision by staring into the eyes of the killer. He obtained a carefully constructed scale model of T-Rex's head. Stevens based his experiment on a simple principle. If I can't see it, it can't see me.
Since I can't be inside the head, but I can look from the outside through this glass sheet, I can figure out how far I can move to the animal's right and still just be able to see the pupil.
To map where T-Rex could see, Stevens carefully moves around T-Rex's head, peering at the creature's eyes. He traces a line marking where he can no longer see the eye. A laser pen spotlights each eye. The glowing eye makes it easier to produce a precise outline. First, he maps how far T-Rex's left eye could see to the right, and then how far his right eye could see to the left. When he finishes, Stevens has drawn what looks like a set of parentheses.
Wouldn't want to find yourself between these parentheses. With a T-Rex there, and it would have probably been sizing you up for its next meal.
Within the red lines is the area where T-Rex could see with both eyes. Scientists call this area of overlap the field of binocular vision, where depth perception is keen.
As plotted here, this is the width of the binocular field of view. And I can turn this into angles. And it turns out for this animal, it's about 50 degrees wide, 50 to 55 degrees wide.
Kent Stevens had his raw data. T-Rex's field of binocular vision was 50 to 55 degrees across. To find out what this might tell him about T-Rex's hunting strategy, Stevens turned to modern animals.
The published figures on some of these raptorial birds is in the 40 to 60 range. So you could imagine T-Rex had as much of a field of view forward as any of these hawks.
Just as a hawk spots, catches, and rips apart its prey, so Tyrannosaurus rex may have prowled the prehistoric landscape with his hawk-like eyes, looking to attack and eat other dinosaurs.
And I doubt that animals have capabilities that they don't use. And I think that the enhancement of the binocular ability, the broadening of the binocular field, is a strong indication that the animal was using it in its predation.
But why is the field of binocular vision so critical to a predator's hunting strategy? It's only within the field of binocular vision that animals can see in depth. To achieve depth perception, you need two eyes, seeing things from slightly different angles. The larger the overlap, the better the depth perception. To see how T-Rex's vision compared to that of other meat-eating dinosaurs, Stevens switched from T-Rex to another carnivore, Allosaurus. Using a green marker, Stevens maps the field of binocular vision of Allosaurus. He finds Allosaurus has only a small field where the vision of its eyes overlap, much narrower than T-Rex. That's because, like alligators and crocodiles, the eyes of Allosaurus are located toward the sides of its head. Therefore, that sideways eye placement would have determined how it hunted.
Allosaurus had very laterally facing eyes, very little binocular overlap. And this, I believe, was an ambush predator.
In order to see at its best, Allosaurus had to turn its head sideways. The raven uses the same tactic because its eyes are also on the sides of its head. The raven must point its eye at an object to get a better look. In contrast, the eyes of Tyrannosaurus rex, like the eyes of hawks and falcons, face more forward. That gives these animals a wider field of binocular vision. Raptors like this falcon can soar high above the ground, searching the landscape for prey. Once they spot something, whether live prey or a swinging lure, they wheel around and swoop down, following their keen eyes in for the kill. Kent Stevens thinks Tyrannosaurus rex had the same killer eyes as a hawk.
I believe that T-Rex then would have been fixed straight down on its prey. It would nonetheless have enough breadth in its binocular field to be able to see the lay of the land, to see how the prey was breaking and moving relative to the surrounds. So I don't think it was like a one shot that would just go out and snap. I think that it could have done pursuit predation.
When Kent Stevens journeys into the Oregon woods and back in time, he looks into the eyes of Tyrannosaurus Rex and knows his worst nightmares are true. He sees an animal with sophisticated vision, a predator that ruled its environment, a dinosaur whose eyes evolved for a single purpose: to hunt and kill. For over 150 years, paleontologists have scoured the globe, searching for the remains of dinosaurs. They've discovered fossil evidence of carnivorous monsters, killers with razor-sharp claws, and giant skulls full of 10-inch teeth. But paleontologist Karen Chin is turning the world of fossil hunting upside down. She's looking at dinosaurs from a whole new angle. Chin searches for fossilized feces, the ancient dung of the dinosaurs. As the world's leading paleoscatologist, Chin knows that this coprolite, a 75-million-year-old dinosaur dropping, may contain age-old secrets about dinosaurs. And to understand how dinosaurs lived, Chin literally cuts through to the very core of their remains.
Well, you know that old statement, you are what you eat. That holds today as it did millions of years ago. So as I determine what the dinosaurs ate, I will be able to put together a food chain and eventually reconstruct parts of the Mesozoic web of life.
Surprisingly, these valuable sources of information have been known since 1823, when the Reverend William Buckland discovered some peculiar rounded formations in the Jurassic sediments at Lyme Regis, England. Buckland realized that he had discovered a new type of fossil, and he named them coprolites, from the Greek word meaning feces rock. Coprolites were essentially overlooked in the scientific community, until now. Karen Chin sees geologic treasures in these most humble of remains. In her former job as a national park naturalist, Chin learned that scat,
Oh, here's some.
or wild animal droppings, offers significant clues about an animal's diet, health, and environment. Chin reasoned that if she could learn so much from the scat of modern animals, why not from the coprolites of dinosaurs that lived millions of years ago? One of the most fruitful sites for coprolite hunting is the Two Medicine Formation in northern Montana. Armed with only a pick and her keen eyesight, Chin hunts the elusive coprolite.
Millions of years ago, great herds of Myhrvold, which are duck-billed dinosaurs, moved through this area, eating, sleeping, and nesting.
And with all that eating, sleeping, and nesting, they were bound to leave something behind.
If you've ever spent any time around animals, say cows on a ranch, or if you've watched elephants at a zoo, you know they produce copious quantities of dung. And they're not particular about where they deposit it. The same would have been true for the dinosaurs.
A Myhrvold was about the same weight as a small African elephant, which produces about 150 pounds of excrement each day. And a herd of 10,000 Myhrvold, over 1 million years, could bury the state of Rhode Island in a layer of excrement 16 feet deep. But with so much feces, why are coprolites so rare?
It takes special conditions to fossilize soft material like feces. These coprolites were probably preserved when they were rapidly buried. This would have protected them from degradation, and over time, minerals would have moved in and fossilized it by turning it to rock.
This area had the perfect environment for preserving fragile feces. 75 million years ago, it was a floodplain. Floods buried the feces in sediment, Then calcium carbonate washed down from the limestone cliffs, saturating the feces with minerals and transforming it into hard rock. But over millions of years, weather and erosion can change the shape of a coprolite, making it practically indistinguishable from other rocks. So how can Chin sniff out a coprolite from an ordinary rock?
Well, I've been looking at these coprolites for many years, so I recognize them pretty easily. But you can see that there are bits and pieces of stem material in here. That's actually wood, and it's all chopped up, so that suggests that somebody's been eating it. So even though this is angular, this is a coprolite. If you look at this rock, now this has a nice suggestive shape, but there's no evidence of any dietary residues on this. So even though this might look like fossil feces, it's not.
But Chin can never be 100% sure if she has a rock or a coprolite until she takes her treasure back to the lab at the Museum of the Rockies in Bozeman, Montana. There she cuts it open, making a very thin slice, which she can then mount on a microscope slide. The clues teased from a coprolite can tell Chin a lot about the prehistoric landscape in this part of Montana.
Looking at a thin section of this slide, we can see a lot of wood cells, wood from a conifer such as a sequoia or a cedar. This tells us that the dinosaur that produced this coprolite ate a lot of wood.
Conifers don't grow here now, so the wood tells her that the prehistoric environment at Two Medicine in northern Montana was much less arid than it is today. Then Chin makes a really amazing discovery. Mysterious burrows, backfilled with a lighter rock, penetrated the coprolite. She determines that the burrows were produced by dung beetles, insects that recycle the fecal matter of migrating herds. This discovery is the first evidence of dinosaur-insect interactions. Eventually, Chin will connect these interactions to reconstruct the whole prehistoric web of life. Until now, Chin studies have dealt mostly with herbivores or plant-eating dinosaurs. But recently, scientists in Saskatchewan found a rare and huge specimen of a theropod dropping, and they called on Karen Chin for confirmation. A team of researchers, including Tim Takarin of the East End Saskatchewan Fossil Research Station, were taking a break from a Tyrannosaur excavation. They noticed some large white blobs weathering out of the gray-green mud.
Wow!
Takarik's team had just discovered the largest carnivore coprolite ever found.
We suspected right from the moment that it was from a large theropod dinosaur, probably T-Rex, but neither one of us are experts in that sort of field. So at that point, we got a hold of Karen Chin.
It is practically impossible to match a coprolite with its creator. But Chin opens a new chapter in paleontology as she tries to solve the mystery of who ate whom. The condition of the bones in the coprolite is Chin's first clue as to who did the eating. Through careful observation, she concludes the bones were not just nibbled and gnawed on, but were actually crushed by massive jaws.
This coprolite tells us that the dinosaur ingested a lot of bone. And because it's all fragmented, we know that the bone was broken up before it was swallowed.
And close examination of the cell structure of those bone fragments in the coprolite gives Chin clues about the victim of the attack.
The dinosaur that was eaten, the one whose bones are inside here, was a subadult. Not a baby, probably something like a teenager, of a plant-eating dinosaur, most likely Triceratops or Apatosaurus.
By piecing together clues from the coprolite and from other fossils found nearby, Chin identifies the perpetrator of the kill, the dinosaur who dropped the ancient dung.
We're convinced that this was produced by Tyrannosaurus rex because of the geological context and because of the great size.
By solving the mystery of who ate whom, Chin confirms another dinosaur's place in the food chain.
For many years, artists have been depicting Tyrannosaurus feeding on Triceratops. That was pure speculation. But now we do have fossil evidence that Tyrannosaurus did indeed eat Triceratops.
Chin's reconstructed world, together with what science has learned from the fossil record, grows larger and more complex every day. Chin looks forward to the time when coprolites will be elevated to the stature they deserve.
Someday I hope that other paleontologists will recognize the importance of coprolites. So when they're out in the field and they come across a fossil, they may say, this is just a bone, but this is a coprolite.
In the future, Chin may be able to detect clues that could help science understand even more about everyday life in the Mesozoic. And perhaps someday, the secrets revealed from coprolites will shed new light on the last days of the dinosaurs.